Greetings and welcome once again to my new calculus channel. My name is John Gabriel. So today I'm going to show you how we got arithmetic right from the very beginning all the way through to the end. In other words, from its geometric origins to algebra. And I'm going to use the prime measure, which is division. Okay, now of course division is formulated on difference and sum. But you'll find out more about that if you study the articles in the detail section. Okay. And you really need to study those articles because what I'm going to show you now is going to be very interesting and you've never seen or heard it before because it's a complete sequence from the beginning to the end. So it's going to take some time. So don't start watching this video unless you have at least half an hour minimum. Okay. Don't start watching it. So let me begin then. Now, if you go to YouTube and you type in something like, how did we get arithmetic in mathematics? you'll get you'll get a ton of videos, okay? A ton of videos. Or more than, well, not a ton, but you'll get a lot of videos. And they're mostly garbage. You'll see this idiot Neil deGrasse. You'll see this idiot. Don't even know what he's doing with basic, how he comes up in this Ben Shapiro, little dimwit. Um, then you'll see another one here, another short. Did we discover or create math? No, we actually create. We actually create. We actually create math. We discover mathematics. We don't create it. Okay, so we discover mathematics, and you'll get thousands of videos, thousands and thousands of videos. Here's another idiot who won a Fields Medal, and Terence Tao, and of course doesn't know anything about numbers or mathematics. Um, there are many, many videos that you will find here that will not tell you how we got arithmetic. Okay? And I'm sure that even after I upload this video, it's not going to come up tops because these already have hundreds of thousands of views. So instead of wasting my time with this garbage, let's just shut it and let me show you how we got arithmetic. So the very first thing that we started with are ratios. Okay, and we used line segments because they're the simplest. Okay, and how we'd represent the ratios is as follows. We'd say let this upward or vertical line be the antecedent part of the ratio and this the consequent. So if you had to write this as a ratio, it would look something like this top part, okay, where you have the red line antecedent and the consequent, okay? So, and the reason we do that is that we want to be able to represent or disambiguate this red length because to different people it might mean different things. Supposing two people came to you, one with ratio B and one with ratio A, and I don't know why it's not showing the label, it should. Right, so if they came to you with these ratios, you may think that this one here is longer or this one here is shorter, but you don't really know until you actually know what they're referring to. And this consequent helps you to understand what this red line means. Okay? That's why you need ratios. Ratio is just simply a comparison of two line segments, this line segment and this one. And it's usually written like I just showed you with the colon, by the way. Colon does not mean divide. It means the first part, which is the antecedent, compared to the consequent. Now, if let's say we want to measure ratio A with ratio B, how are we going to do that? We can't just say, let's take this antecedent and measure this one because they're not the same. Okay, it's like trying to say, let's measure these oranges using these Lego bricks. Okay, they're two totally different things. In other words, they need to have the same consequence, which are the blue lines. Right? How do we do that? Well, we do that using parallelism, and we go back to one of the very first mathematicians. Thales is his name in Greek, Thales, and he used parallelism. So through parallelism, let me just move this back here. Let me do this. Through parallelism, what we try to do is we find another ratio for A which has the same consequence as this one. And that's very easy to do because all we do is we take this, join these two ends, a line like that, okay? So it would be something like this. It would be something like this, right? And we just carry on moving it across until we get the full ratio, okay, which is the new ratio, which is this ratio here now. And as you can see, once you've found a common consequent, it turns out that this ratio A is actually uh, ratio A actually has an antecedent bigger than ratio B, right? So it's important that you don't make any assumptions about ratios until you see the consequence, right? So now we've got the consequence, and now we can easily measure ratio A with B. And what does it mean to measure ratio A with B? It means to divide this line by this line. That's what it means. So to do that is very easy. We simply find the resulting ratio. And what's the resulting ratio? It's just this line as the antecedent and this line as the consequent. So in geometry, this is the division of ratio A by ratio B, where this red line is this line and this blue line is what this red line became. It became the consequent, okay? So now we've actually found the division, the resulting ratio of division. Now, so far, this is all geometry. And for example, if this distance here was pi and this distance here was square root 2, this would be the exact result of division. Because in geometry, arithmetic is always 100% precise. But what do we do in algebra? Okay, in algebra, we want to represent these ratios with numbers. In order to do that, we have to find how to determine a line segment that fits into both this antecedent and this consequent. And the way we do it is as follows. So we take this very same one that I showed you earlier, and then we take the difference between this line and this line, which is just basically this little red line, and then again the difference between these two, which is this blue line here, right? And as soon as they're the same, we know that we've found a common line segment. The next step, my friends, is to use that as the unit to count the number of equal parts in each of these ratio members, okay? So, and the way we do that, we say let this be 1, okay? This unit to itself be 1, let this be 2, let this be 3, and now we can count 1, 2, 3, and 1, 2 here, right? Look, 1, 2, 3, and 1, 2, okay? Does that make sense? Okay, so going back to this now, we see that in geometry, we can do this using something called Book 5 and Proposition 12, where we use the more primitive operations such as difference or sum. By the way, sum is defined in terms of difference, and it cannot be done the other way around. So when we use that, we're using similar triangles. We're saying take this value here over this value and just simply keep on increasing until we can turn this bottom part into what's called a whole number, 4 over 1 and 6 over 1 on the top. and then we can further simplify it. And you can see how to do all this stuff in these articles that I'm going to put in the details section. Okay, that's what I'm going to do. I'm going to put these articles in the details section, and this one here is very important: essential mathematics, measure and number. But I would first read this, because this will set the stage for you to understanding the next book and the solutions in the next book, which I suggest that you go through every single one of them. Otherwise, you won't understand. And this knowledge shows you now how to go from right from the beginning all the way through to algebra. Okay, so you end up with this measure. In algebra, 2/3 divided by 4/9 is 3/2. And isn't that what we got when we did it geometrically? Yes, look. Why, look here, look here. 1, 2, 3, 4, 5, 6. Okay, that's 6. 6 over 1, 2, 3, 4. 6 over 4. But that's what we have here, isn't it? And then, of course, we could easily say that's the same as minus, uh, and if we find a similar fraction, it's going to be this, isn't it? Minus 2, and that's going to leave us with 3/2. Okay? Which is what you find over here. So I've shown you now, by the way, how to go completely from geometry all the way through to algebra. And you don't get to choose this knowledge, by the way. This knowledge is not created, it's discovered. It exists whether you ever thought of it or not. Okay? It's perfect knowledge. It's only possible because a genius like I revealed it to you. Am I proud of it? Oh, heck yes. This is something I didn't understood at least until the age of 24. And none of you, nobody after Euclid and before me understood. How do I know? Because there's nothing out there published which tells you what I'm telling you right now. Okay, so if you're not already a subscriber to my channel, this channel here, please become a subscriber. Don't post crap comments on my channel because most of you are morons. I'm sorry, that's true. So please don't post unless you have a question, and only one question at a time, because I don't see very well, I have limited vision, and I don't like to spend time on the computer, so I probably won't answer your comment or even publish it if you have a lot of questions. You can find all your answers in the resources I give you. You have to study, okay? These things don't come easy. They require hard work and effort. Very well, then you can also support me at my GoFundMe page, right? Or you can join my members only channel for $4.99 a month. It's like buying me a cup of coffee every month. So the choice is yours. That's pretty much it. My name is John Gabriel. This is a new calculus channel. Till next time, goodbye.